Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Ilya Levitsky. Ilya received his bachelor and master degrees in applied mathematics and physics from Moscow Institute of Physics and Technology. Currently, he is a researcher in wireless networks lab of Institute for Information Transmission Problems, and he is working towards his PhD degree. Ilya created a first ever prototype of non-orthogonal multiple access Wi-Fi device. Ilya is also a voting member of IEEE 2.11 committee that develops and standardizes Wi-Fi technology. He authors a dozen of papers and patent applications. Today he will present us his recent results on evaluation of capabilities of the Wi-Fi chips used in modern devices. Ilya, the floor is yours.
Thank you, Vyacheslav. Hello, everyone. It's a pleasure for me to participate in this seminar once again as a speaker. And today I will present you a talk called False Protection of Real-Time Traffic with Quieting in Heterogeneous Wi-Fi 7 Networks. This talk is based on the recently published paper with a similar name, authored by me and my colleagues Andrei Barannikov and Evgeny Khorov. Today I will mostly follow the content of the paper, but occasionally we'll add some extra details for clarity and for the completeness of the story. So let's start. And the story starts with one of the most, probably the most controversial topics in wireless networks, latency. You might have heard that you should never be gaming over Wi-Fi because of lags. And this is something that academic community wants to fix. There are a lot of application types out there apart from gaming that still require real-time operation at some degree. Remote sensing and control, virtual reality applications, and so on. We all are probably familiar with the fact that keeping the latency low using wireless networks, especially in the unlicensed spectrum, is indeed quite a challenge. So one method that could partially help is enhanced distributed channel access, or EDCA for short. EDCA is already widely spread in modern Wi-Fi chipsets, and it differentiates between four access categories that have different priorities when competing for the channel access. So EDCA can reduce average latency for voice and video traffic, yes, but it is still based on random channel access. Hence, there is a non-negligible probability that the transmission of an urgent packet will collide with someone else's frame, or will be unfortunate enough to lose channel access competition multiple times in a row, driving the urgent data in the queue outdated. Hence, not just average latency needs to be reduced, but the worst case latency needs to be reduced. And for this reason, the developers of the new standard of the upcoming Wi-Fi 7 technology, the standard is named IEEE 802.11be. So the developers propose a way to address the requirement for low latency, and even in its project authorization request document, the group developers have stated that the, quote, amendment defines at least one mode of operation capable of improved worst-case latency and jitter, end quote. So IEEE 802.11be standard in its current form specifies a mechanism named restricted target wake time, or R-TWT, that would specifically tackle the low latency problem. Let's review how R-TWT has emerged and how it works. The story of R-TWT starts in 2016, when the first mechanism, regular target wake time, has been introduced there in the amendment 802.11ah. This amendment is for the Wi-Fi Hello technology that is designed for the Internet of Things. And the IoT devices need to basically save energy. So they would periodically switch off their radio interfaces and back on when required. For that, Wi-Fi Hello station will negotiate with its access point the schedule of being awake and doze. And when the right time comes, for example, when the beacon is transmitted or a regular transmission is expected, the station will wake up at the target time, switch on the radio, and proceed with the reception or with the communication in general. Thus the name, target wake time. And the time during which the transmission occurs is called service period, as shown here on the slide. The stations that are scheduled to awaken during the service period are called members of this service period. And I think that is enough details for us for today. So the core idea of target wake time is pretty simple, and it was later reused in 802.11ax to enhance the spectrum utilization. It would not only be energy efficient for the stations to use this mechanism, but it would also ease the contention between them. TWT service period can also be leveraged for a multi-user transmission, as you can see here, further increasing the efficiency, which was the eventual goal of the 11ax amendment. For that, at the start of each service period, the access point transmits a trigger frame that solicits data from many stations, for example, in an OFDMA transmission. That's just one example. After that, the developers of the new standard, IEEE 802.11be, realized that TWT can be slightly altered to turn it into a new tool that would reduce latency. The key difference is that the members need to use R-TWT service periods for a specific category of traffic associated with low latency. And that the other stations that are not members of this service period are restricted from carrying out any transmission that would cross the start of the service period. They can either finish their transmission before the service period starts or begin it after it starts, if the channel is not physically or virtually occupied, of course. I will make a quick note here that there's been a concern of why R-TWT should work this exact way. For example, why not to restrict non-members from ever transmitting inside the service period? But simplifying a bit, it was just decided to be a good balance between the latency guarantees for the RTA stations that have real-time traffic and maintaining a performance for regular stations. So we have a new R-TWT mechanism that is destined to improve worst-case latency and jitter as well. The members of a service period will transmit data inside the service period, and they will have a higher priority of initiating the transmission at the start of the service period, because all other non-member stations that support 802.11be will not transmit during this time. And I wonder if you can find a flaw here. I said that only 11be stations will respect the restriction, because older devices will simply not understand the new mechanism. Those would simply intervene with the new service period. So that's a problem because new Wi-Fi 7 networks will be heterogeneous too, as modern Wi-Fi networks are. There will be devices from various generations, not only from Wi-Fi 7, but existing devices will participate in those transmissions too. So how would one silence the devices of previous generations at the start of the service period? So the chosen solution is quieting. The quieting is the mechanism that should be supported by older stations because it has been invented many years ago. And the access point can announce that the schedule for those quiet intervals that overlap with the start of the R-TWT service periods. And then the stations, even older ones, shall refrain from transmitting during those intervals. R-TWT11BE stations react to quieting as well, but if quieting is overlapping with some R-TWT service period, they will simply ignore it. So let us briefly review the details of the quieting framework in 802.11. As I said, it was done many years ago. It has been specified in the standard in 2003, and it is a part of the dynamic frequency selection framework. This framework is used to detect signals from other devices, such as radars, that could interfere with the channel. And the access point would need a way to detect such signals and take some measures. For example, relocate the entire network to the different frequency. To detect such channels, access point would order all stations to stay quiet for some time, while it scans the channel for interference. So this is an effective way to make all stations in the network silent. And as I said, quieting intervals are typically not signaled per instance, but in a periodic manner. The schedule for the quiet interval is communicated through so-called quiet elements that are typically included in the beacons, which are periodically broadcast by the AP. The quiet element includes 4 fields. The first one is quiet count, that specifies the number of beacons left before the next quiet interval. The second is the quiet period of the number of beacons between quiet intervals that are periodic. The third one is quiet duration, and this is literally the duration of the time to stay quiet. And the fourth one is quiet offset, which is measured from the target beacon transmission time to the start of the quiet interval. And the last 2 values are measured in so-called time units that are roughly 1 millisecond long. So, of course, to ensure that all devices obey this mechanism, the AP can make it mandatory in the network by enabling dynamic frequency selection. To do that, it would raise a spectrum management flag in the beacons and maybe some other management frames. And then the AP can reject all stations that would ask for association but do not support this feature. So going back to the use of quieting intervals in the R-TWT mechanism, we saw that only the start of the service period needs to be protected. So 802.11be prescribes to protect the service periods with quiet intervals with a fixed duration of 1 time unit, not to waste too much time. And if multiple service periods are scheduled, like in this picture, the respective schedule of multiple intervals described by multiple quiet elements is created. So where is the conflict in this story? Yeah, from the standards point of view, everything should work okay. Everything is stable and viable. However, the problem arises when it comes to the practical implementation. The first suspicion is that quieting is not a very popular mechanism. The 82.11h standard amendment is not a major one, and the scenarios where an access point would need to relocate network to another frequency using DFS procedures do not seem that ubiquitous. So quieting may simply not be implemented widely, which would mean that our R-TWT mechanism would practically not be able to use it to secure the service periods. The second suspicion is that even though the standard defines how quieting should operate, that doesn't mean that the device manufacturers implemented this in the same way. To be specific, they can have some broad understanding of how quiet framework works, how it should work. And for example, 8P would ever so often create some quiet interval of several tens of milliseconds of duration to scan the channel for the interference. And it will do it very rarely, maybe once a second or maybe even more rarely. And that is very different from what was described in the previous slides, where a very short quiet intervals are used, and they are used very often, multiple times during a single beacon interval. And this is exactly what R-TWT needs, because it would serve some practical real-time traffic, like virtual reality, for example. And the final suspicion there could be simply bugs or even intentional misbehavior of devices when it comes to quieting. Because streaming a lot of data is very tempting, even if an access point says to stay silent. And we know of this misbehavior from our previous works. We did some research that is related to the actual behavior of real off-the-shelf devices, and some other research by other teams has been done as well. For example, the papers 1 and 2 here reveal that real devices perform carrier sense differently from what is standardized. And such a deviation is actually widespread. Not only that, there are issues of coexistence between modern and legacy devices that was also discovered. For example, in papers 3 and 4. There, authors consider cases when legacy devices partially or completely disrupt the work of the new Wi-Fi mechanisms. So these works show that such cases are widespread. So the reasoning, this reasoning motivated us to check how quieting actually works in modern devices. And would there be any problems when R-TWT mechanism comes to the market? So first, we have reviewed what already has been done in the literature regarding quieting. And to be fair, the information is scarce. Papers mainly focus on possible attacks on the networks using quieting. For example, papers 5 and 6 examine several devices with various Wi-Fi chips and operating systems to see how they react to beacon forging. The beacon forging is basically using an attacker's device to send copied and modified beacons with malicious intentions. For example, setting up a schedule of frequent and very long quiet intervals, which would paralyze the communication in the network. And some devices in their results did get affected, but some didn't, and some did partially, which is a sign that there is a different implementation of quieting framework in the devices. But these papers do not give a sufficient insight into how the devices would react to real, that is, non-forged beacons, with a quieting schedule that is suitable for R-TWT. And also, the papers are quite old. As you can see, one of them has aged about 10 years or even more now. So implementation has probably changed since then. However, the networks have advised us a very interesting point, that the behavior of the devices depends on operating system and not only on chip hardware. So quieting is also investigated in the paper 7, but it was for a completely different purpose. It's studied for contention reduction, prioritizing, and distributing traffic. So no consideration of short quiet intervals in any sense that would be useful for R-TWT. So there were not very much relevant papers that would say how quieting could potentially cooperate with R-TWT. So we understanding that there is a gap that we needed to fill. So to proceed, let's specify what exactly we want from the quieting framework to qualify it as a valid protection for R-TWT service periods. The first and the obvious step is that quieting support should be signaled in the devices. That is, the respective flags shall be raised when the device associates with the access point. Quieting is an essential part of dynamic frequency selection framework, as I said previously. And in the standard, it is said that a special flag called spectrum management should be raised when the DFS, or dynamic frequency selection, is active. So by that flag, we can judge whether the station supports quieting or not. And the next step is also very simple. The station shall stay silent roughly at the time specified in the quiet interval in the beacon. This can be just a simple interval, once every beacon interval, for example, with a duration of, for example, 20 time units with an offset of 30 time units. Pretty average one. Then we want the station to perform short 1 time unit quiet intervals scheduled inside the same beacon frame very precisely. That is, it shall not deviate from the requested position too much, because otherwise it might not even cover the start of the service period. Finally, the station shall follow multiple quiet intervals scheduled inside the same beacon interval. And that is essential from the practical perspective, because for real-time traffic, we expect frames to arrive multiple times inside a beacon interval. So many R-TWT service periods would be required for that, and each of them shall be protected with a quiet interval. So how would you test this behavior? The simplest idea is to set up an access point to broadcast quieting information with the parameters that we want. But it turned out to be quite a challenge on itself. The access points that we had at our disposal did not simply allow performing quieting at all. And we could, in theory, hack into them and change their drivers, but that seemed to be very time-consuming at the moment. So we were lucky enough to find in somewhat short time a device that actually does something close to what we want. At least it can set up flags that we want in the beacons. This is the AP called Aruba AIP 207. And for this find, I'm actually very thankful to my colleague, Andrei Barannikov, who has actually found this access point. So, Andrei, thank you very much for that. Still, there was an issue that an access point has a setting to turn on or off the quiet elements, but it has no settings of the quiet intervals themselves. That is, you cannot specify the duration and the offset of them. And the default operation of one quiet interval is that a single quiet interval is broadcast every 200 beacon intervals with a 20 time unit offset and 30 time unit duration. And we could not change it. And as you can see, we even changed all the configuration in the access point as was specified on the site. So we turned on the quieting, but no further than that. We could not specify the details of the parameters of the quiet intervals. So to overcome this issue, we decided to develop the following testbed, inspired by the idea from one of our previous papers. We introduced a software-defined radio, USRP, in the testbed. USRP would serve as a transmitter of the modified beacons with the quiet element set up as we would like it. But implementing all access point functionality in USRP is quite hard, so we implement the following idea. Our testbed has 4 devices: a Wi-Fi device that is under test, a monitor on the left, an access point, which is our Aruba AP on the top, and the USRP, the software-defined radio. The monitor here is a MacBook Pro laptop with a packet sniffing program Wireshark that captures and analyzes frames sent in the channel. The Aruba AP sends beacons every 100 time units, that is the duration of the beacon interval, associates new stations, including the device under testing, and does all the AP stuff, basically. So the USRP does the following at the start. In the beginning of the experiment, it works in the monitor mode. It receives beacons from the AP and saves them. And then the Aruba AP is switched off. Immediately, the USRP detects that there is no more beacons in the in the network. So it takes its place and sends beacons on the behalf of the access point. The content of the beacons from the USRP is the same as those from Aruba, except for the added quiet elements and recalculated frame checksum. So the device under test should operate as usual. At least we expect it to be, and you will see that that is exactly what we see. So the device under testing should transmit UDP traffic as we have configured it. And the USRP will acknowledge those frames sent by the device. And during the experiment, we settled on the UDP traffic since it does not generate any transport layer acknowledgements, and thus there is no unwanted downlink traffic, only uplink. So for each experiment, we would record all the frames by the monitor that are sent in the channel, and we'll process them later to find the frame intensity. The frame intensity is the number of frames sent by the device under test to the AP per every time unit. So we can break all our recording, that is multiple seconds long, into beacon intervals. And we can do the following. We can subdivide all the beacon intervals into 100 time units and count the number of data frames that is received from the device under testing during that time unit. And then we can average that data across all the beacon intervals in the recording. And in this example, you can see that after this averaging, we get this frame intensity. So in this example, you can see that the quiet interval should behave. The quiet interval should make the devices behave in the following way. The device stays silent inside the quiet interval, so frame intensity goes to 0, and it stays at somewhat high value outside the quiet interval. So we have tested a variety of devices with different Wi-Fi chipsets and operating systems in this way. And based on our analysis, we have identified 5 groups of devices with different behavior. The first group, Group A, consists of Apple devices, which run Mac OS and iOS operating systems. And these devices indeed have the spectrum management flag, so test 0 passes. So we expect them to support quieting framework, hopefully in accordance with the standard. However, only test 1 passes successfully. If the AP advertises only 1 long quiet interval per 2 or more beacon intervals, everything is okay. But if the length of the quiet interval becomes 1 time unit, the position of this interval within the beacon interval becomes evidently inaccurate. And we do see that if there would be a service period that would start, in this case, at the 29th time unit, the frames would have crossed the start of the service period. On top of that, if the AP advertises a single quiet element in every beacon interval, every second quiet interval is ignored. And a similar problem would occur if there were 2 quiet intervals inside the beacon interval. The first would be respected, all the following ones will be ignored. And there are multiple ways to interpret this behavior. For example, possibly due to an oversimplified implementation of the quieting framework. Specifically, the devices from group A could store information only about one quiet interval, that is the first one broadcasted by the AP, and to remember all the following ones, there is simply no allocated memory. So they just ignored. The group B consists of several Android mobile devices based on Qualcomm system on chip. And similar to devices from group A, they also indicate quieting support, but they do not support the advertisement of multiple quiet elements too. Even during the test one, we discovered that the quiet intervals are only executed correctly if their period is at least 10 beacon intervals. That is, if a quiet interval is requested more often than once per 10 beacon intervals, that is approximately, well, like a long duration, the device may accidentally ignore some quiet intervals, which is an unwanted behavior. Group C consists of Android mobile devices that do not support quieting framework entirely, although some of them may raise the spectrum management flag. For example, during association, a device Xiaomi Redmi Note 4 indicates that it does not support spectrum management and quieting framework. But in contrast, one of the Huawei smartphones claims to support spectrum management but never remains silent in any tests. So we assume that the absolute absence of quiet interval is connected with some misconceptions about spectrum management implementation, and the vendors might implement spectrum management partially, but to support a different mechanism other than the dynamic frequency selection. So the fourth group, Group D, that we included in our set of devices to be tested, actually has only one device, and it is equipped with Qualcomm Atheros Wi-Fi chip. And interestingly, the results for this specific device depend on the operating system. In particular, the device under test running Windows does not care that it supports spectrum management and does not avoid transmissions during the quiet intervals in the tests. The device that is operated by Linux, however, authenticates with the AP with the raised spectrum management flag. However, it incorrectly estimates the quiet interval position, while the quiet interval duration is still correct. So you can see in this example, the quiet interval should be here, but the device stays silent at the completely wrong time. So the final group is Group E, and it consists of some laptops with Intel Wi-Fi chips. And like in Group D, the support of spectrum management flag depends on the operating system. But in any experimental scenarios with any considered operation system, quieting framework just does not work. So let us sum up our results. From the obtained experimental data, we conclude that the majority of tested devices do not support quieting framework entirely. And we can see that only Group A devices have passed the test one successfully. But other devices either do not react to quiet intervals at all, or even though some of them may signal the respective support, or do support it, but the support is very imprecise. These findings actually are very unfortunate, also considering that none of the devices even closely passed the test 3, where multiple quiet intervals are requested per one beacon interval. And this makes a quiet sync framework a questionable tool to enhance protection for R-TWT service periods. If a Wi-Fi 7 access point emerges today and uses R-TWT service for a, say, VR station in coexistence with modern devices, we would predict that R-TWT might have an effect close to none in terms of latency improvement. Broadcasted quieting schedule would simply not be respected. Surely, considering some extra restrictions, we could make R-TWT work, but only if the service periods are requested at every 2 or even every 10 beacon intervals, which is actually very impractical. So the question now is, what should we do? Surely we want the happy end for the story, right? So indeed, there are possible ways to go. One direction is using self-CTS frames for channel reservation. And virtual reservation of the channel is actually a very powerful backward compatible tool, but it may cause high channel waste in many scenarios, where less resources to reduce the resources wasted, we could modify the mechanism that stands behind the self-CTS frame transmission, but it would definitely require additional changes to the standard, and they are likely not to be included in the Wi-Fi 7 standard, but in the following one for the Wi-Fi 8 technology. So, and of course, some would say that R-TWT can still be used in the dedicated channel where there are no legacy devices, but I can say that you can judge the practicality of this solution by yourself. So there is no obvious set in stone or obvious solution as of yet, but we aim to find one. So let me say a few words in the conclusion. For your information, the IEEE 822.11 interim is going on right now as I'm speaking. And during this week, there have been several TGBN slots. TGBN is the group that actually specifies what the Wi-Fi 7 will be like. And in those meetings, the coordinated AP scheme is being elaborated, and a substantial amount of proposals reuse R-TWT idea for the AP coordination. So the schemes are being named coordination or coordinated R-TWT. And if the basic R-TWT would not work efficiently in real cases due to the misbehavior that we found, why would the coordinated R-TWT? So I believe that taking and talking about this problem is very essential, including in the IEEE working group, and that is what we actually would like to do. In the end, the goal of this research and this talk as well is to bring the attention to the issue and encourage the community, both the academia and the industry, towards finding the solution to this problem. And we hope that we've done so well. Thank you for your attention.
Thank you, Ilya, for your interesting presentation. We have several questions in the chat, and the first one from Professor Andrei Lyakov. And the question is, was the quieting certified by the Wi-Fi Alliance?
The quieting mechanism is specified in the 802.11h amendment. Here it is. Yes, so it was specified, and it was a part of the dynamic frequency selection framework. So the developers of the 802.11be relied on this framework to be active in modern devices, and so they decided to use it as a foundation for R-TWT.
Yeah, maybe I will clarify the question. From my point of view, certification and standardization is quite a different things. That maybe some standardized feature are not included in the Wi-Fi certification. So Wi-Fi developers may ignore some features of the Wi-Fi. And the initial question was, okay, we understand that quiet is standardized, but is it required to achieve Wi-Fi Alliance certificate?
Okay, thank you for the clarification. Yeah, I just misunderstood it. So the certification is probably something that has happened because we see a lot of regulations brought up at the meetings that regarded dynamic frequency selection. And we did see some references to dynamic frequency selection, not only in the code of several implementations, but also in some documents. So I cannot reference you directly to the certification, but I believe that this thing should be certified and something to be very strictly looked after, especially in the Europe.
Okay, thank you. I think we can go to the next question from Mikhail Lubogoshev.
Yeah, thank you, Ilya, for your very interesting presentation. I have the following question. So, what do you think of Wi-Fi 6E generation? Because as far as like in my understanding, or more correctly, I would expect the vendors not to rely on the previous generations of Wi-Fi, saying that okay, nothing will work there. Thus, let us really implement the new features in the new spectrum, where there are no obsolete devices. So 2 points of questions. First, whether you think that 6 gigahertz interval will work, and the second one, did you have any chance to test it?
So I will start with the second part. We did not test 6 gigahertz because we were not able to make our access point to operate in that band. So we did not figure that out yet, but this is something that we probably technically could do if we had the proper access point. So we need to find the access point that both supports the new band and also has some control over quieting framework. As to the first part, in Wi-Fi 6E, well, that is basically Wi-Fi 6 that comes before Wi-Fi 7. So if those devices that will use 6 gigahertz devices will be legacy compared to Wi-Fi 7 devices, both access points and new devices that support R-TWT. So it is true that the new band will not be as populated as modern 2.4 and 5 gigahertz bands, but still some devices will be there, and the behavior of the exact behavior of these devices in that bands is technically still a question, as I said at first, but the intuition says that everything will work typically the same.
Yeah, okay. Thank you. I just hope that maybe the developers did think a bit about that, and when updating the chips to the 6E generation, they would have added this functionality.
Yeah, let us hope for that together. That is actually what will enable R-TWT with more confidence.
Thank you. The next question is from Anton Karamyshev.
First of all, one thanks Ilya for the interesting presentations, and actually I have a series of questions related to the modality on the application, how the stars should follow these rules about the unquieting. And first of all, could you clarify, does the standard, I mean 11H, 11K, or 11AX, mandate the unquieting procedure? I mean, should the star follow it in the obligatory manner or not?
Okay, I see. So the answer is no. Not all devices are obligated to support quieting, but quieting, as we can see in the standard, is an essential part of the dynamic frequency selection framework. So if the access point mandates, and it has a right to mandate any mechanism that it wants, and reject from association any device that does not support some specific mechanisms. So if the access point mandates dynamic frequency selection, including quieting framework, we can see that access point can mandate using quieting in its network. And this is exactly what we did in our experiments. We tried access point to mandate this behavior, and even though a device is successfully associated with the access point, they still have shown signs of misbehavior.
Let me clarify a bit on my questions. Let's assume that all devices, I mean the AP and the stars, set up or enable the flag on the spectrum management. The star may follow the quieting framework, or they shall follow it.
If they signal spectrum management flag, devices shall support quieting. As for
okay, I believe, yet I have some doubts on that. Please double check it.
Yeah, that is actually one of the important parts of our research. We actually scanned the standard to make sure that that is how we imagine. Because if that's something that's not correct, that's a big fault from our research team. But we can ask some people to check that too, if they're interested.
To this work, yeah. Okay. The second question is then similar to that. And can you go to the slide with specifications, with the functionality of your AP Aruba?
AP, yeah.
I'm a bit wondering about the last part of the second sentence, because this is stations may not transmit, which is may.
Let me see. May not transmit. Okay. So I suspect that you are triggered by the word may, not shall. But
the modality again, yeah.
Yeah. So I assume that this is not a standard. This is not a standard text, which means that they are not strict about the exact words that they say, because in regular English, may not actually is the same as must not at any case. So this is my hypothesis.
Okay, maybe in a bad time a bit thinking. Let me say that it main means that then star may not follow the rules. And this is bad. Okay, and then the third question, and I hope the last one, would you clarify the situations in the B upcoming standard? For example, if the AP and the stars have an agreement on R-TWT usage, in that case, does the quieting procedure is the quieting procedure in that case mandated for these devices or not?
Once again, is the quieting mandated for devices that
in the case if these devices have an agreement on R-TWT usage? Yes.
So first of all, if devices are members of R-TWT, they ignore quiet intervals. That's something that I said. Regarding the mandation of quieting interval support, I'm not sure about that exact statement in the standard text, but it is something that I think should be implied, especially if the device is designed to work to support R-TWT. So that might be specified in the text, but I cannot tell for sure right now by the memory.
Okay, and thanks. And finally, I have a small comment aligned with the question from Andrei Lachov. And probably the certification procedure on Wi-Fi 7 may contain a procedure, an experiment in which the devices are not tested for R-TWT support, and this procedure may contain quieting element support. So we may hope that certified Wi-Fi 7 devices will support this.
Yeah.
Do you agree on that?
I agree that new devices will support quieting with higher probability, but the main question of this topic is what should we do with existing devices? Because Wi-Fi networks are heterogeneous, and devices that are in the market right now that do not necessarily support quieting, they will intervene with the new mechanism, and this is the question. What should we do?
Yes, I agree. Thanks.
Okay, thank you.
Thank you. And the next question from Andrei Belagaev.
Yes, thank you very much for the interesting talk. And also, to be honest, we have recently cited your paper. And to be even more honest, I didn't knew about this paper before one of the reviewers pointed our attention to that. So, which is a bit of shame because we were the same group, but this happens. So yeah, the research is really interesting, but during your talk, my attention was really triggered to the thing that you mentioned about how the R-TWT actually works. That after recent talks, discussions, they decided that the stations should not cross the R-TWT boundary, but the stations that do not belong to this R-TWT can actually start transmission inside R-TWT.
Yeah.
And you said that for short there is a trade-off, and this decision was as a result of the trade-off. But I don't really get the trade-off, because I think that today there are a lot of projects and a lot of attention on wireless TSN and determinism in wireless networks. So allowing stations that do not belong to the negotiation to transmit actually hinders the determinism and hinders the support of wireless TSN. So can you maybe elaborate a bit on that?
Yeah, okay. So first of all, I will state that I'm a person who was actually also very skeptical about this decision, but we get what we get. But I can describe the motivation that I've heard so far. And the motivation is approximately as follows. So R-TWT service periods actually have the goal to increase the priority of the members to have access to the channel with higher probability. But that does not mean that the devices will actually use the channel, because they simply might have no data at the time. For example, R-TWT may be set up for quite some time, but at the moment, for example, the user has stopped the application and there is no data streamed. So not to waste the channel time, if the legacy devices or 11BE device that is not the member of the service period detects that service period has begun, but no data is detected, it may as well be available for all other devices. So that is a way to keep other devices at relatively high performance if real-time devices stay silent.
And is it already in the standard, in the written form of the latest draft or not?
Yes, it is.
Well, it's really big news for us, because we were thinking that there is great attention nowadays to the private networks when, for example, people that do Industry 4.0 or 5.0 or whatever 0, they will rely on the private setup where there are no legacy or obsolete devices, and they actually can control which devices are in their environment. And then they will rely on the implementation of Wi-Fi 7 of the robots or other chips that are other devices with Wi-Fi chips. And if the standard will allow interruption of R-TWT, then you could not actually implement TSN with this R-TWT.
Actually, Andrei, if you said that the projects rely on the fact that the channel is free from any legacy devices, there will be no problem that you described. There will simply not be any other devices that are legacy. There can still be devices that are non-members, but if the vendor or the company controls the behavior of all the devices, that probably
no, it's not the case. I mean that you have a company that wants to establish a setup for, let's say, small fabric with Industry 4.0 devices, and they all have commercial off-the-shelf chips with Wi-Fi 7. And of course, you cannot control what is implemented in these chips. But if you would rely that once you establish R-TWT, then no one will interrupt the stations that were assigned to this R-TWT, that could work. But if you say that a standard actually allows the stations that are not inside the agreement to interrupt, that's a pity.
Yeah. Okay, Andrei, I see that we have quite a conversation here. I think that we can continue further.
Yeah, I'm sorry.
Yeah.
Thank you.
Yeah. Thank you very much for comments.
Thank you. The next question from my side, and as I understood from your talk, the quieting framework is a part of DFS, which was initially, as you said, developed to ensure that some other devices, non-Wi-Fi devices, are working in the channel like radars.
Yeah.
And as I know, DFS requirements in different countries and in different channels may be required or not. And my question is, in which channel, in fact, do you perform your experiments, and which channel was set in the which country was set in the settings of the access point, and whether the regulatory requirements of this country in the channel require the DFS.
Yeah, actually, Vyacheslav, you are asking the right questions. There is indeed some specifics about what rules shall be followed in different channels and in different regions, and I cannot recall all the details for our experiments, but I'm pretty sure that we paid some attention to what types of what countries were signaled in the access point, and we made sure that still the devices will associate with the access point successfully. And there was different behavior on different channels, but I cannot remember exactly what was the difference. Perhaps quieting was not supported by the access point itself at all at some channels that were not specified as those that would need dynamic frequency selections, something like that.
Okay, I got your answer.
Mm-hmm.
So, any more questions? So I guess that's all for today. Let me thank Ilya for interesting talk, and also all other participants for fruitful discussion. See you in the next seminars. Goodbye.
Thank you for having me. Goodbye.